Okay, so let's have a brief recap of what we were doing. So we finished up with our discussions with rotations, but I just want to remind you that what we've discovered is that the Lie algebra of rotations is crucial in understanding the rules for multiplication, the algebraic rules for multiplying rotation matrices. So in 3D rotations, otherwise known as SO3, I would like to write it as SO3, like that. What we discovered was that there are different ways to describe the Lie algebra. One is to use the double index notation, but this can be related to the single index notation. This is unique to 3 dimensions, and the Lie algebra is what's important here. Is that they commute, they do not commute, and in fact they give you the following algebra. So this is also related to this is the SO3. This is also related to the SU2 Lie algebra. So I'll talk more about it once we start talking about spinors. But essentially what we discovered was that if you use the Pauli matrices that you might be familiar from quantum mechanics, they obey exactly the same commutation relations. So here you would identify one of these guys as JA, the correspondence, right? It's not globally, I should mention, globally they're not the same thing. Turns out that SU2 is what's called a double cover of SO3. But, and this, for example, is the reason why when you rotate an electron, it doesn't quite come back to the same state. You pick up a minus sign. So those who have taken quantum mechanics before might be familiar with this fact. But I'll come back to this again when we talk about it. So that's where we were in, as far as talking about rotations were concerned. And I just want to bring it up again as a brief recap, because this is going to be important, right? It's going to be important for understanding rotations. And the key point here is that whenever you have a Lie algebra like that, J squared, which is just JA, sum over A, and J3 are good observables, right? So they are the observables that we usually use. In particular, the J squared is going to show up even in the Marantz group. So what we do is we label our states by L and M, and J squared is going to turn out to be L times L plus 1, Lm. And J3 is the eigenvalue of this. Let me just emphasize the J squared term. So L can be integer or half integer, 1/2, 3/2, and so on. And so we're going to talk about the Marantz group. We already started talking about the Marantz group. What you will see is that the integer guys are related to bosons, and the half integer guys are going to be related to the fermions. And there's a deep connection between this spin, and also later on you'll see what's called statistics, which is that fermions cannot occupy the same quantum state, but bosons can. Right? This is something that you're told in quantum mechanics, but is not shown to you. So there's this deeper there's a deeper formulation behind this that we will see maybe in a few weeks from now. when we start to quantize the fields. But anyway, this is where I want to leave our discussion on rotations for the time being. And then what we did was we moved on to Lorenz Symmetry. And so let me also briefly recap where we were there. So actually, do you mind turning on the AC for me? Thank you. So we started by asking what is the distance between, we had a similar discussion for space, but let me just skip that and just go straight to the space-time case. So you have a space-time point x. I should say sometimes I use x just as a shorthand for the coordinates, right? So that I don't have to keep writing it. Sometimes I'll write mu if I want to. And then I displace it slightly, and I ask, what is the distance between these guys? And it turns out that the distance is described by what's called the line element. And for now, I'm going to add the c here, but very soon I'm going to drop it. And this, remember, takes this form. And so there's a difference between the time and the space part. The time has a plus coefficient, and the space part is all minus. Okay, so in the literature, it's now more common to write it the other way around. So let me just write it down for once, and you guys can see. It's more common these days to write minus c squared dt squared plus dx dot dx. Right. And so there's a metric convention way to write this. So I can write this as g mu nu dx mu dx nu. And g mu nu is just the notation for the coefficient of the quadratic differentials. Right? And so in our case, that's actually a special symbol. If you are in flat space, then there's a special symbol, theta nu dx mu dx nu. And if I set c equals to 1, then eta mu nu would simply take the form 1 minus 1 minus 1 minus 1 if you are in four dimensions. Okay? So this is in 3 plus 1 dimensions. If you are in fewer space dimensions, then you just have fewer minus 1s. If you have more, then you just have more minus 1s. Okay? And if you use the opposite sign convention, then here your eta mu nu will be minus 1, 1, 1, 1. Again, if you have 3 plus 1 dimensions. Okay. This is more common these days. So if you look at the older quantum field theory books, for example, Pascal and Schroeder uses this sign convention that I use. But relativity books tend to use the other sign convention, but the newer books in QFT also more often uses this. Weinberg, for example, if you look at Stephen Weinberg's quantum field theory books, I believe he uses the mostly plus. I should say, yeah, this is called the mostly plus convention, and this is called the mostly minus. Sometimes people use the word signature, but it's a little bit, I think it's a little too cryptic. Right? Just say mostly plus or mostly minus, and people understand what you're talking about. Okay, so I told you how to measure distances. And oh, before I move on that, let me just remind you what C equals to 1 means. Okay, C equals to 1. What does that mean? So remember, I've told you guys before that as physicists, you want to try to be as lazy as you can, okay? But you want to be able to get away with it. If you don't get away with it, what that means is you make serious errors, right? Because of your laziness. So this is not one of them, okay? So this is, of course, I'm half kidding, but there is a reason why you don't want to carry the symbol C around. And let me remind you this, because in fundamental physics, C shows up all the time. In fundamental physics, whenever you deal with relativistic situations, this will show up all the time, meaning this symbol will show up. And because of that, you don't want to keep carrying this symbol around in all your calculations. It's very cumbersome. You see it all the time, you carry it throughout all your calculations, and more often than not, you will make a mistake when you carry your factors around. So that's the practical reason, right? You don't want to make mistakes. But the sort of more fundamental reason is because C is such a fundamental object in physics, you want to measure everything related to speed with respect to this base unit. So let me just say this. So this is, in other words, you're using C as base unit for speed. Okay? Because it is the fundamental, or maybe the ultimate speed, as you guys know, right? It's the ultimate speed. In nature. Why it's like that? I don't know, right? 299,792 meters per second. That's what it is in SI units. Why is this number in SI units? I don't know. But it is what nature is. And so when we deal with physics in relativistic situations, we measure all the other speeds with respect to it. Right? And so, for example, when I say V equals to 0.1, without telling you, without writing down C. Now, if I just have to tell you that this is a speed, so that actually means that V is actually 0.1 C. That's what this means. Right? So it gets some. You have to get used to it somewhat, but once you get used to it, then everything is much easier. So for example, if C is 1, then you notice that meters is equals to seconds, right? So in other words, 1 is equals to 299,792,458 meters per second, right? Which means that 1 second is in fact this number of meters. In fact, by the way, this is in fact how we define the meter these days, because we can measure time very accurately these days. Right? We have this cesium atomic clocks. So 1 meter is defined as the distance that light travels in 1/299,792 and so on of a second. That's actually how, if you look up, this is now how we define the meter. It used to be some bar in some museum in Paris, or I don't know what happened there. But now that we can measure time very accurately, we use the fundamental constants to define our units. Yeah. Okay, so that's a short blurb about C equals to 1. When we get to H bar, I'll have the same or maybe I'll tell you guys now, right? So this is a side. I want to get back to Lorenz symmetry. So, but let me as well tell you guys about H bar. Okay, so the other thing that we will set to 1 very often is H bar equals to 1. Okay, so H bar, I don't remember the numbers, but H bar is, you can look it up. By the way, if you want to look at all these fundamental constants, there's a nice place compiled by particle physicists, pdg.lbl.gov. And then if you just search for physical constants, there's a review, there's a page on review articles and so on, and there's a whole, I think there's 2. Files. One is physical constants, and the other one I think is for astrophysics. But these days, there's a lot of cross activity. So if you want to look up constants, that's a good place to look up. So if you look it up, you will realize that H bar is in terms of, it will tell you some joule seconds. Right? So this is actually energy times time. Whereas C is, of course, speed, which is length over time. So when you set C equals to 1, let me summarize that first. When you set C equals to 1, means I'm setting length equals to time. Okay, because of that. And let me just tell you first what happens. When you set H bar to 1, that basically means you are setting time equals to 1 over energy. Okay? So of course all these things look ludicrous, completely ridiculous, right? If you enter a physics 101 class, you just start doing physics, and then your professor comes in and say energy is 1 over time. Length is equals to time. And then you think this professor is crazy and you just quit physics, right? How come NCU employs crazy professors? And that's why we keep until graduate school. Then we tell you crazy things, right? Because hopefully then you're stuck already. You can't, it's too late. You can't quit physics now, it's too late. So, again, I've already told you about C, so you know that it's only a joke that I'm crazy. I'm not really crazy, but it's really, a way to, for you to emphasize what's important in your calculations, right? And just as C is very important in relativistic physics, H bar is extremely important whenever you do anything quantum. Right? So anything quantum, you will see H bar. In fact, this is usually the 0th order check that we do when we try to figure out, is an effect you are calculating, is it quantum or is it classical? What do? You look for factors of H bar in what you are calculating. If there are H bars, then it's quantum. If not, it's probably classical. But although sometimes it's subtle, sometimes the H bars cancel out. Right? So it can be a bit subtle. And of course, the problem is that if you set H bar to 1, how do you know whether you have H bars or not? Right? How do you know if something is quantum or classical? And this is where you need to know what you're calculating. Okay? But anyway, let me just finish this. So H bar turns out to be as I always like to remember, is the fundamental base unit for action. This is a little bit more abstract than C. C is the fundamental speed in nature. But if you tell a freshman, action, what the heck is this? So action is something that you learn when you take a more advanced course in classical mechanics, for example. Right? So for example, what's the action for that you often see in classical mechanics is the integral of kinetic energy minus potential energy. Okay? And where the x is the trajectory of your particle, right? And so when you vary this, and you will find that if you demand that the variation, this action is stationary when you vary the trajectory, then you'll find that what guarantees the stationarity of the action is Newton's second law. So you get ma equals to minus gradient of v. But I mean to say this only for two reasons. One is that we'll see this again when we talk about field theory, because ultimately what's going to be important for understanding field theory are the symmetries behind it. This is why we should talk about symmetries. In terms of the action, is a very useful way to get at the symmetries of the field theory. But the second reason is that this is the action, and you can tell there's a time integral, and these are energy. Right? So you can tell that this is actually energy times time. And it would turn out that if you later on will learn something called a path integral, which I hope you've seen in the quantum mechanics course. If you take my quantum mechanics course, I will certainly tell you the path integral. But essentially you'll find this object will show up. The analog of this object, so in quantum mechanics, in fact, something like that would show up in an exponential. It will turn out to be I times S, and what divides it is h bar. Okay, and this is why I call h bar the fundamental base unit for action. In other words, all the actions that you ever cook up in physics, when you do quantum mechanics, it will be measured with respect to h bar, quite literally, because you're dividing by it. So what happens is that in quantum mechanics, you end up summing over, I'm just going to be very rough here, you're going to sum over all axes, all the trajectories that your particle can take. And it turns out that when you sum over all of the paths, this is a wildly fluctuating factor, because it's oscillating I times something real. It oscillates, right? And because it oscillates rapidly, it turns out that through something called a stationary phase approximation, you find that the path integral, this object, is dominated by the classical path in many situations. Okay? Again, it is meant to be a rough description of what's happening. I will talk about the path integrals in the field theory context probably a few weeks from now. But the point is, whether or not this is a wildly fluctuating factor is controlled entirely by how large h bar is. So if somehow you live in a different universe with a different value of h bar, then the size of quantum effects will be different because the action is now divided by a different number, right? If you live in a different universe, h bar might be different, and then the size of the quantum effect will be divided by some constant that is different from our universe, and so quantum mechanics will behave a little bit differently. But this is the reason why h bar is so fundamental. It's key to understanding how to understand whether your dynamics is classical or quantum. So the key question is the dynamics classical or quantum? And that's the measure, which is you divide the action which controls the dynamics by that h bar. Okay. So the summary again is when you set c equals to 1, what you're saying is that you're choosing your fundamental unit for speed to be the speed of light. And as a result, now length is basically equals to time, or there's at least a correspondence between them. And then when you set h bar to 1, because h bar itself is energy times time, so energy is inverse time, or time is inverse energy. The other way to remember is that, maybe I'll remind you guys, the energy of a photon, remember, is h bar omega. Okay, so when h bar is 1, the energy is the frequency. And frequency, remember, is basically 1 over time. Okay. So that's how I remember the energy goes like 1 over time. Any questions for me? Oops, video stop. Yeah. Yeah. Yeah, so it's the kinetic energy minus the potential energy integrated over time. There's a time dependence here, right? So basically, yeah, this is I don't, it's not a classical mechanics course, but it goes like that. Usually you fix your initial position, okay, and your initial time, and then you fix your final position and your final time. And then what you do is you ask the question, when you integrate your trajectory, you integrate x of t, plug into this expression here. So everybody here depends on time. And this depends, v is dx dt delta into itself. All of them depend on time. When you integrate from the initial time to the final time, but you demand that the endpoints are fixed, and you ask the question, what happens? So every time you can cook up any trajectory you want, okay, and then you can plug it in. But this is a number, right? You plug in your kinetic energy minus your potential energy, and then you do an integral, right? Maybe you have to do it numerically. But in any case, it'll give you a number. The question is, what's so important about this number s? The number s is important because in classical mechanics, when you ask which part extremizes s, you'll find that the answer to this question is the classical part. It's the part that obeys Newton's laws. Yeah. We've not seen this before. Have you seen this before? Okay. Yeah. So s is the action. It's a number, but it's a number that depends on the part. So it's not a function, but a functional of the part. And I just And this entity is called the space-time metric. Okay? And so now I'm going to talk about why this is important. Right? And I'll answer your question, what is indices? The H-bar discussion was a side remark, but it's important because we want to do quantum field theory. Now, so what is special relativity? Do you have a question for me? No? Okay, so special relativity is the following statement, that you want that inertial frames are frames where that's your metric. Okay. And what happens is that you want to find a transformation that will relate different inertial frames. So number one, inertial frames are frames where you find coordinates, Cartesian coordinates, where this is now your metric. And furthermore, when you have two frames, two of such frames, two inertial frames, let's say x mu and x prime mu. Again, the index here just means which component you're referring to. Now, what you'll discover is that they can be related in the following way. X mu equals to lambda mu nu x prime mu plus a mu. And let me explain what's happening here. So, firstly, let me remind you the Einstein summation convention here now tells you that these guys are now summed over 0, 1, 2, 3, right? In 3 plus 1 dimensions, that's what's happening, and that's what we'll be doing mostly. But in general, we can run it to d minus 1 in d minus 1 plus 1 dimensions. Okay. Then now comes the physics. What do these guys mean? So it will turn out that these matrices correspond to what you would call Lorenz transformations. Okay. What you have learned in undergraduate physics, hopefully, that these are your Lorenz transformations. And for us, this actually includes both the continuous and discrete transformations. So this will turn out to include the rotations that we talked about. It will include the boosts that you learned from undergrad, hopefully, but also time reversal and spatial parity flips. So this is what this one includes. So it includes a wide class of transformations that relates one inertial frame to another inertial frame. And then a mu itself corresponds to basically space-time translations. Okay. So if I move from here to there, but at a fixed time, then a mu would only have space components, not time components. But in general, I can have both displacements in both space and time. Okay. So what is so special about these transformations is the following. remember that I want to go from inertial frame to inertial frame. And inertial frames themselves are defined by your metric looking like this eta mu. So that means when you go from frame to frame, this transformation had better preserve this metric. Okay? And this is also why I did the rotation. I did the rotation case first. So remember that rotations preserve the metric in flat space. Right? So how do I see that? Because dl squared in that case was dx dot dx. And when I rotate my displacements, I get back the same thing. Okay. So likewise here, what you find is that, let's take the d on both sides, you get d x mu equals to lambda mu nu dx prime nu. Okay. And because it's a constant, right? I'm assuming that all these matrices are constants. And when you plug it into the metric, remember this guy is, let's say, if x is an inertial frame, then I can plug this into this metric. But what would it look like? You look at eta mu nu, and then here I'll get lambda mu alpha dx alpha. Okay, I'm now summing over alpha because I already have a mu here. And then this is, oops, I'm sorry, there's a prime here. And then lambda nu beta dx prime beta. So remember this is dx mu. This is dx nu. Okay, and I can now collect my factors together. And I get eta mu nu lambda mu alpha lambda nu beta, and then dx alpha dx beta. Okay? And so the demand is that if I want to go back into an inertial frame, a different inertial frame, then we want to obtain the same thing, but now with respect, I'm sorry, there's a prime here. We want the same thing, but now with respect to the prime frame. So eta alpha beta dx prime alpha dx prime beta. Okay, so let me emphasize, the prime frame is not the same as the unprime frame. You're in a different inertial frame, but the metric is the same. In other words, if you are in an inertial frame, you can't tell whether you're in one frame or another frame. This is, physics in all inertial frames are the same. And that's the starting point. How do you guarantee that your physics is the same in all inertial frames? You make sure that all your notions of length and distance and time, all this is the same regardless of which inertial frame you are. And that's the statement here. If you are in the x frame, you have eta mu nu. If you are in that prime frame, you still have eta mu nu. still the same metric. Okay? So that means now we have, just like in the rotation case, remember rotation was defined, this statement can be converted into this index notation. Right? This is the definition, or at least one of the starting definitions of rotations. The other one is that the determinant of R is 1. Right? These two things form what we call rotations. Likewise, the definition of Marantz transformations is that for the metric to be preserved, you want your Lorenz transformations to preserve the metric. Okay, so this is in fact the definition of Lorenz Group. And in fact, so suddenly I tell you it's a group. So in fact, the same proof that I went through for rotations that showed you that it's a group would also apply here. So I think I'm not going to do it because I've done it for rotations. Right? So you have to step through there are only a few axioms that define a group. Right? So if you're interested in checking your own understanding of what a group is, you should step through for yourself. I think it actually is in my notes, but you should step through for yourself. Starting from this definition, that all lambdas that satisfy this equation is an element of the group, you can show that in fact they do satisfy all the necessary axioms. Okay. Okay, so now let me try to answer your question, because now that I've talked about, actually let me finish one more thing, which is that I have gone one way. I've gone starting from here. I've shown you that if lambda satisfies this, then you are going from inertial frame to inertial frame. Right? There's a closely related question, which is that if I start from an inertial frame, right? So if I start from this question, but if I don't restrict myself to this transformation, if I don't restrict myself to this transformation, if I try to find out what's the most general transformation that will give me back eta mu, right? So let me just say this more generally. You can let x mu be some function of x prime, right? And what will happen is that if you start from here, you will find that dx mu will just become dx partial mu partial x prime alpha, dx prime alpha, and then partial x dx nu will become partial x nu, partial x prime beta, dx prime beta. This is now your ds squared. And if you start from this more general premise, and you ask, you still demand that you want to get this. You want to get this. It will turn out that the most general transformation that you can cook up is in fact this guy. Okay. So I showed you the easy way. I gave you the answer, and I showed you that as long as you demand this, then you will go from inertial frame to inertial frame. But if you try to be more general, if you say, let me solve for the most general coordinate transformations, you'll find that that's the most general answer. Okay? So the proof can be found in my notes, which actually is borrowed from Steven Weinberg's general relativity textbook. Okay, so if you are interested, again, you can look at that. But it's quite technical, so I'm just going to skip it. But it's worth noting that the most general coordinate transformation is in fact given by that answer over there. Remember, yeah. So remember Lorenz transformation plus space-time transformation. Oh, I forgot to say. So Lorenz transformation is just this part. But if you add space-time translation, that's where the word Poincare comes in. So Poincare means Lorenz plus space-time translation. And this will turn out to be important, even in quantum field theory. The representation of the whole group, not just the Marantz group, but the representation of the whole group, Poincare, is going to be important for our understanding of how to classify particle types. Right? I will at least sketch the argument. I don't think we can go through the whole detailed argument, but I'll try to do what I can. But this is why we're building this out. Okay, so again, before I forget, let me answer your question of indices. Right? So because of the existence of eta mu nu, and because eta mu nu has a sign difference in, I already erased it, but let me write it down here. There's a sign difference between the time and the space. It's actually important to realize that the indices position, when you talk about space-time tensors, is important. Okay? So,
should we require the determinant of lambda equal to 1?
Yeah, I'll come to that. Yeah. Not yet. So when I define my Lorentz transformations, this is my definition. Right, and remember, I wrote down in words. This includes rotations, boosts, and also time reversal and spatial flips. Yeah, and that means that I'm also including determinant equals to -1.
But when we write down
for
when we
rotation,
use the chain rule, then we recognize the transformation is
no, you can,
Sure.
right? I mean, you can let xi equals to minus x prime I, right? No problem taking the derivative here. xi over x prime a is just minus Kronecker IA, for example. Right? No problem. Yeah. Yeah, it includes everything. For now it does. Time reversal, flips, and so on. Yeah. But when we start doing the Lie algebra, then I'll have to focus on the continuous part. Okay. So the position of indices. So either up or down is important. Okay, so let me tell you the rule first, and then as we go along, I will explain why. Okay. So in general, we will deal with Lorenz tensors. And these guys can have many indices, but let me start with just a vector. Okay, a vector for me, actually I should call this a one form, but for this course, we can be a bit sloppy about it. Okay, a vector for me just means a one-index object. Now, there's a difference between, when I say the position is important, there's a difference between this guy versus this guy. So how do you relate the two? You use the metric. So if this is upstairs and you want to bring it downstairs, you have to contract it with a metric. Okay? And if you want to go the reverse, so if this is up and you have a downstairs, then you must use the inverse method, which we haven't talked about. But the inverse method is given by just this same symbol, but with the upstairs index. So I better explain the inverse method. So this is supposed to be the inverse of eta mu. But thankfully it's simple enough that you understand how to do it. Right? So this guy is 1 minus 1 minus 1 minus 1. So of course the inverse just means you want to multiply this to get 1, right? Which is 1, 1, 1, 1. But because that is diagonal, you find that numerically this is exactly the same thing. 1 minus 1 minus 1 minus 1. Right? Because when you multiply this guy to this guy, you get identity. But it is important to distinguish, this is the upstairs indices, and this is the downstairs indices. So it's important. So that when you go from upper indices to lower indices, you have to make sure that you contract it with the metric. And when you go from lower to upper indices, you have to contract with the inverse metric. So for example, in flat space is very easy. For example, if you go to from the zeroth component, which is prime, right? This is the prime component. You can relate this to the guy with lower indices through a contraction. But because this is 0, so this is 0, right? But I have to contract it with the lower index guy. But remember, this is diagonal. This is a diagonal. Everybody is 0 except when the indices are the same, right? So basically, this is telling me that the only thing that can happen here is eta 0, 0, A0. Okay? Because it's diagonal. And eta 0, 0 in my convention is 1. So A0 upstairs is A0 downstairs. But remember that, so this is in mostly minus. Okay. I will only remind you guys at the beginning because I'm not going to use the mostly plus. But in the literature, you will find that if you find the mostly plus convention is getting more and more common. Okay, so in mostly plus, this is what will happen. And then remember that I use English alphabets to denote my spatial components. Right? So I use Greek to indicate my space-time indices, but Latin or English alphabets for space. So this would be eta I, so I can be 1, 2, 3 basically. Alpha, A alpha, and again it's diagonal. So the only thing that it can be is eta II, AI. Okay? But eta II in my case is always minus 1. So it's minus AI. So it's actually very easy to remember. If you're raising a time index, it's just 1. It's the same. If you're moving a space index, you will cost yourself a minus sign. Right? So either going from down to up or down to up to down, right? It will be a minus sign. But for the mostly plus convention, there's no difference for the space, but for the time there's a minus sign. Okay? So depending on your application, if you want to distinguish between time and space, you have to make sure you keep track of your minus signs. If you are trying to say something more general, then you want to make sure that you have taken into account either your metric, if you're going from up to down, or your inverse metric, if you're going from down to up. Any questions for me? Yeah. Yeah.
So the A substitution means this represents the Mills component of this vector A.
That's right, exactly.
And for this substitution,
Yeah, it's a Mills component of this thing. But But the difference between these two objects is that there's this, you can think of it as a matrix multiplication, right? This matrix multiplied by this component, this bunch of components, give you this guy.
So in the sense that you
Yeah.
can get two components by these
Yeah.
transformations.
So let's do it, okay? So this is A0, A1, A2, A3 is equals to 1 minus 1 minus 1 minus 1 mu contracted with this is the mu component, right? And then A0, A1, A2, A3, right? And then from here we get A0 minus A1 minus A2 minus A3. Okay, let's start. Yeah. Epsilon, I'll come to this a little bit later. Yeah. One thing at a time. Okay, so epsilon, I'll come to that.
Wait a minute.
Yes. Oh, okay. I won't erase it then. Okay, so before I go on, I want to mention, somebody should ask me, right? Why in the world is it important to have a sign difference between time and space? Okay, and so this is in fact the key reason that made us discover that time and space should be related through one single entity called the metric, right? Space-time. Why do we call it space-time? It's because of this. And it is important for the following reasons. We have already seen that when you relate different frames, different inertial frames through Lorenz transformations, what you find is that if this is your unprimed frame metric, in the prime frame, you can write down exactly the same thing. Just put a prime on your coordinate. Right? So again, they're not the same thing, but the metric is the same. Right? And this is the Lorenz invariance that is so key to special relativity. Okay? And this tells you the following. So firstly, I should mention some jargon. Right? So when df squared is positive, that means that dt squared is greater than dx squared, which means that the displacement in time is greater than the displacement in space. So we call this time-like. When df squared is less than 0, that means that the displacement in space is now greater than the displacement in time, and so we call this space-like. And when dx squared equals to 0, that means that dt squared equals to dx squared. And this is sometimes called like, which I'll explain in a second. Or sometimes it's called null. Okay? Like or null. And this is the key. Okay? So remember that dx squared takes either this form if you're in this inertial frame, or this form in the inertial frame. It turns out that light takes null parts. Okay, so actually this itself requires explanation, but you have to believe me for now. Right? But this is the realization that Einstein had, that if this is true, then what happens is that in one frame, in the x frame, you have dx squared equals to 0, which means what? Which means that dt squared equals to dx squared, which means you can take the absolute value on both sides, and you see that dx, the absolute value of the displacement divided by dt, is 1. or you should put back a C, because you know this is a speed, right? This means it's C. Okay? So if you assume light takes null paths, which is this one, then immediately you find that the speed is 1. Now let's go to a different frame, the x prime frame. And remember that these are related through Lorenz transformations. But again, if I always assume that light takes null paths, yeah, so it's given by the Variance Transformation itself. In fact, it's given by this guy, which is why I had to work this out. And what is it given by? It's given by lambda, alpha, mu, partial alpha prime. Right, so alpha prime. So when I put an prime on my index, this means dx prime alpha. Okay? And it's given by this guy. But then you can ask the question, what happens, what about the differentials themselves? Okay, and this is going to be an example of lower versus upper index. Okay, so this is a lower index, and you notice that it transforms like that, right? When you go from the derivative with respect to x to a derivative with respect to x prime, you contract it with this Lorenz transformation, which is actually the inverse of the original guy, right? That guy is actually the inverse of this guy. But now let's look at this guy, for example. What happens here is that by the chain rule, this is dx mu dx prime alpha, dx alpha. Okay? And this guy is given by this guy here, which is lambda mu alpha dx prime alpha. So you see that the lower index object, this is the first example, okay? The lower index object transforms like this in terms of the inverse transformation. Whereas the upper index object, which is actually why we write our coordinates with the upper index, because when you take the infinitesimal transforms as the Lorenz transformation. Okay? You see, this is not the same, right? We have to be careful that this is not the same object as this. It's the inverse of each other. In particular, what we showed just now was that mu alpha mu beta equals to Kronecker alpha beta. Okay. What you can also show is that if you contract these two instead of these two, it's also the inverse. Okay, so let me write it down. So mu, and then alpha, you should find that it's also Kronecker mu. The inverse, whether you contract them this way or that, you contract them using these pair or this pair. You will get the identity. And the reason is because both are Lorenz transformations. The transpose is also the Lorenz transformation. Okay. So this is an example. So let me just say it before I forget. Okay. So in general, alpha indices transform oppositely from lower indices when transforming or when going or switching, how about that? Switching between inertial frames. So that's the reason, that's the key reason why we distinguish between upper versus lower indices. And that's why it's very important to make sure that we treat them appropriately. Now, there's another question, which is how is it related to our contraction with the metric, right? So I think I'm running out of time, but let me say the main point first, which is that the contraction of the metric, in fact, will cause your tensor to transform oppositely from what it used to. So let me say that, and then you see whether we have the time to demonstrate this fact. So for example, let me start with an object. Oops, I should use that alpha equals to larger alpha beta, x prime beta plus a alpha. Let me start with an object like that. Okay? And the reason why I want to include the x mu is because now I view this as a single object. And now I see that when I switch from x to x prime, what happens is I get a alpha, so there's a sum over mu, and then x will now be replaced with, actually let me forget about a for the moment. X will be now transformed to x, lambda applied to x prime, okay, and then this guy will be mu alpha dx alpha. And so, now I can view this as a function of x prime, but now I also have the components of my original tensor are now contracted with the Lorenz transformation matrix. Right? So in other words, a mu of x is related to a mu, so sorry, let's say that properly. So let me say it again. So, but this is now the coefficient of dx prime. So I can define this to be a alpha prime of x prime dx prime alpha. That's how I think about tensors. I contract my indices with the infinitesimals, if it's a downstairs index. And now the mu component is to be viewed as the coefficient of dx mu. Just like here, the alpha prime component is to be viewed as the component of dx prime alpha. Okay, and so now I can say, what's the transformation group? A alpha prime, which is in the x prime coordinate system, is in the prime inertial frame, is related to, so this group, the a mu component in the x coordinate system, provided that you substitute the correct group, you substitute this group, and then you contract the components with the correct Lorenz transformation matrix. Okay, so this is your first tensor transformation group. Which means that if you have a tensor, in this case just a one index tensor, once you know it is a tensor, then you can relate the components in different inertial frames in a well-defined prescription. Okay? And that's how you do it. You just basically treat them as Lorenz vectors, and you contract them to the right Variance Transformation matrix. Okay. Now, how do you think about the upper index guy? So for example, A mu of x. So it turns out that the upper index can be thought of as a directional derivative. So when you have an upper index, what you should think about is that it's actually an object, one object, contracted with the partial derivative. And because of that, you can now do the same trick that we did, which is to go to a prime coordinate system. So we can now do a mu, and then you plug in x and replace it with lambda contracted with x prime. And then this guy, you have the Jacobian, but I won't repeat that argument again, because we know that this is going to be mu alpha. Okay? We did this just now, so I won't repeat this argument. And so now, in terms of the prime coordinate system, now you can view this as A alpha prime x prime d alpha prime. Okay, so the definition is the coefficient of this derivative. So that the reason why we do this is so that this whole thing is a geometric invariant. It's the same form no matter what coordinate system you use. Right? It works even in closed space-time, but we won't go there. But the point here is that, again, you see that the upper index object is related to each other. If you are in the x coordinate system, you substitute the x prime definition, and then you now contract it with the opposite Lorenz transformation. Now this is up, down, this is down, up. Right? So this is not the same thing as that. But then, once you have done that, then you have converted this upper index object into this upper index object, but now in the x prime coordinate system. So again, this is the tensor transformation rule. This is for upper index. So just for lower indices. And this is for tensor transformation for upper indices. And you can show that if you start from a lower index guy and you contract it with the metric, this will transform as an upper index object. Okay? So I guess we should do it, right? So let's do it. So this is now going to be let's start from, so we always go from prime to unprime. So let's start from the prime index. So the prime index is this object. How does this transform? Well, this is A mu of x, but substituted for lambda x prime. And then this guy, we know, has to transform like mu beta, alpha. And then alpha beta. And this is the final view that, therefore, this is actually now a mu of x prime lambda mu beta. And remember, the rule is that I can view this as a upper index if I consistently move my indices with the metric, then this is now mu data. Just as this is actually data prime x prime. So what have I shown? That the upper index, if I move the indices with the inverse metric, that's in fact consistently transformed like the opposite. This guy down up is opposite of the up down. Right? So this transforms oppositely from this just because I raised the index using the inverse metric. And likewise, you can show the same thing. If I ask the question, how does this guy transform? You'll be able to show that this guy transforms like a lower index object. Okay, I won't do that one, but you get the idea. And then the other thing is, what about if I contract two indices? Okay, so if I contract two indices, then I have to form a scalar because of this important statement here. The reason why, again, we distinguish upper from lower indices is because when you contract two indices, you form a scalar, and you don't have to do any transformations. So let me finish that part and then we'll end that. By the way, we're missing some classes, right? So I will have to teach a bit longer each time because I didn't want to have a makeup class on a Friday. I'm assuming nobody wants to. Sorry, on a Saturday. So I'm assuming nobody wants to come back on a Saturday. So my plan is I'm going to teach a bit longer, maybe 10 minutes each time, and then by the end of in a few weeks, right, we'll have made up the two classes. I think we're missing two classes, right? Last Friday and this Friday, yeah, which is 100 minutes, right? Yeah. So over 10 classes, right? 10 minutes, we need 10 classes to make up for it. Yeah, I think we can do it. Okay, so let me finish with that, okay? If I have an upper index object contracted with a lower index object, and I do a transformation x going to x prime, Lorenz transformation, then we know what's going to happen is that because they are related to Lorenz transformations, this guy is going to transform like the forward, right? This is the upper index guy, so it's going to be let's go, let's go. So mu alpha, right? And then this will give you W nu, and then this will be nu alpha, like that. Okay. And because these are inverses, they will give you connector mu nu, and therefore it's just V mu prime W mu prime. So whether you calculate it in the x coordinate system or the x prime coordinate system, all you have to do is just treat it like a scalar. So it's a scalar. Okay. Now, let me finish with one last thing. In your homework, I believe you will work out the wave operator. And let me finish with this. If you believe that the wave operator is part of your physics. Okay? So in fact it is. Let me do it on a scalar. This is the wave equation. If this is the equation in the X frame, and if you believe that physics has to be the same in all inertial frames, then I don't have to do any calculations to find out what the physics should be in the X prime frame. It has to be the same form. So it has to be X prime wave operator acting on phi of X prime equals to 0. In other words, it must take the same form, just that the coordinates are different. Right? But if I'm in just this inertial frame, I don't know about this. As long as I'm in this inertial frame, that should be my law. Right? If this is some law of physics, that's my law of physics. If this is the law of physics in my X frame, then it has to be that if physics is the same in every frame, I must be able to do a Marantz transformation and find that I can get from this equation to this equation. Okay? So this was related by Marantz transformations. And for the scalar case, because this phi here is just a function of x, there are no indices on it, so I'm assuming it's a scalar. The key to showing that it is in fact related to a Lorenz transformation is your homework, which is that under a Lorenz transformation, you find it's exactly the same form, meaning partial alpha, partial beta contracted with the inverse metric is partial alpha prime, partial beta prime contracted with the under Lorenz transformation, you'll find that they are related. And this is the beginning of what we mean when we say that the laws of physics are Lorenz covariant. That's why I don't want to use this word covariant versus contravariant. Because for me, covariant means the physics statement that the laws of physics take the same form no matter which inertial frame you are in. And the reason and the way we do it is to make sure that the form of the equation transforms in a very well-defined way when we go from one frame to the other. In this case, it's a scalar. So you have to take the same form when we go from x to x prime. If it's a tensor equation, then the indices must match up through the Marantz transformations. So we'll do the tensor case in later classes, but at least now you see, this is the first example of what it means to have a covariant set of laws for physics. That it must take the same form in both inertial frames, and you can calculate and show that it really is related.
I'm a little confused because why, if it's the same form, why do we call it invariant?
In this case, it's also invariant, but when we do tensors, they're not invariant in the sense that they're not the same object anymore, but they are actually, there will be transformation rules that you have to. So for example, later on when we do the photon, when you choose the Marantz gauge, it will look like this. Okay? And then, of course, when you go to the x prime frame, what will happen is that it will look like this instead. Okay? So, because there's an index here, this alpha is not mu prime. This mu prime is not the same as this. Because this mu prime is related to this through a Lorenz transformation. So it's not the same object, but there's a well-defined set of rules that allows you to Lorenz transform between the components in different frames. And that's what we mean by covariant. So it's not invariant, but covariant. Right? Invariant means it's the same. Right? And you're right, that in this case it's invariant, in the sense that it's the same scalar field, takes the same form, But of course, we have to remember the coordinates are not the same. But otherwise, yeah, it's invariant because it's a scalar. But in this case, it's a covariant set of equations, not invariant because it's tensor. Yeah. Good. Any other questions for me? Okay. See you guys next week.